9.5, note we are talking about functions and their inverses, so we're using some of our old content. Do you guys remember the vertical line test from way back when? I mean, you literally draw a vertical line, right? And it tells you if a graph is a function. And that was a really quick check, wasn't it? So the vertical line test determines if a relation is a function. And I'm abbreviating function. Now, the rule was the vertical line test could pass no more than 1 point. So any vertical line can pass no more than 1 point on the graph. If it passes no more than 1 point on the graph, then we know we have a function, okay? So I'm going to jump down here before I talk about this horizontal line test and talk about these graphs. So I'm sliding this down. It says, determine if the relation is a function and explain. Okay. Is this original graph a function? Well, if I draw a vertical line, do we agree that it hits more than 1 point? So the relation, what is given, is not a function. And it's not a function because it fails the vertical line test, which we use as VLT. Okay, how does the vertical line test connect to that definition of a function? And what was the definition of a function? I'll start. Function. Every x, do you remember, has, it's been a while. I mean, it's been a long while. Every x has exactly 1 y. Good. So when we were looking at exactly 1 y, when we were looking at tables, we would look to see if the x repeated, and if it did, we only have one outcome. Now, we're all focused here. No one's on their phone. No need for a calculator right now. So when we're looking at this, when you go through this vertical line, when x is at -2, we found a y value of, I don't know, 2.8. I'm just estimating. And when x is down here at -2, we have a y value of maybe -1.8. And so the idea is that x value of -2 has more than one y value. Okay, and anywhere I draw a vertical line except for the vertex of this, what that would happen with. So the relation is not a function, it fails a vertical line test. Now what about this guy? Are there any vertical lines I could draw that hit more than 1 point? Now, I think no matter what I do, every vertical line passes. So the original graph, the relation, this one is a function. And again, I'm going to abbreviate that FCN. And it passes the vertical line test, which basically tells me every x has exactly 1 y. All right, now these two graphs are considered continuous. They don't have arrows on them. Even if they stop, they're continuous between points. This graph is considered discrete. So these two graphs are continuous, just throwing out some terminology we've used. And this graph is considered discrete because it does not continue between 2 points. Now, do you see as soon as I try drawing a vertical line right here, I get the point of what? -2, 3, but I also get a point of -2, 1. So this is not a function. It fails a vertical line test. Would it have failed the vertical line test anywhere else? Yeah, right here. X is 1, it has 2 y values. So the relation here is not a function, and it's not a function because it fails the vertical line test. You have to be able to back up everything you're going to say. Now, that's old news. We've already done functions. Today we're focusing on inverses. So an inverse is basically flipping your x and y. And that's what we're going to talk about. So we're jumping right in here. It says here, the horizontal line test, which we'll abbreviate to HLT, the horizontal line test passes through more than 1 point in the graph, then the inverse relation is not a function. So the horizontal line test is test the inverse. Now, here's the deal. When I find an inverse, I have to flip the x and y values, which flips the graph. So if you're looking at an original graph, and I have, so here's my xy, and I have a point. I better give you a couple dots here so you can just sort of look at my experiment here. And I have a point at 1, 3. The inverse of that point at 1, 3, its inverse is at 3, 1. The idea is that you go across this line of symmetry for reflection. So inverses reflect over the line y equals x. So whatever my y is, I flip with my x, and that creates an inverse. So you get this butterfly pattern, but it's over the line y equals x. And this is that line that always got people. Guys, y equals x is the same as y equals 1x plus 0, right? Start at 0, up 1 over 1, up 1 over 1. No matter where I go on this line, 1, 1, 2, 2, 3, 3, 10, 10, -5, -5, whatever x is, y is. And so inverses flip over here. Now, instead of having to create an inverse, so the inverse I would have to create over this dashed line, I would take this and I would flip it, and it would be that upright U-shaped parabola. But instead of flipping my graph, I just flip my test. That's the idea. So when I'm physically looking at a graph, that is the relation. Is this graph a function? No, it fails the vertical line test. But if I ask you about the inverse, I'm going to do the horizontal line test. No matter where I draw a horizontal line, do you see that it's never going to cross more than one point? So the inverse is a function, and that's because it passes the horizontal line test. Okay, so I'm not flipping the graph, I'm flipping the test. Why am I flipping the test? Well, vertical line is x equals, right? We're focusing on, does x have more than one outcome? The horizontal line test is testing the y equals. This is y equals 1. And I can't have more than one y for every x if I'm thinking about the inverse. All right, so looking at this one, let's talk about it. The original one is a function because it passes the vertical line test. Rather than having to flip my graph, can you picture this being folded and my graph flipping? I'm going to flip my test. In the horizontal line test, now this has an angle coming down, so the horizontal line will only hit one point there. So this one is also a function because it passes the horizontal line test. There's no relationship between if the original passes or fails the vertical line test. So here you have not a function, but the inverse is. Here you have the original is a function, and the inverse is. Now, does this one pass the horizontal line test? I'm going to go with no. So it is not a function. Not a function because it fails the horizontal line test. So that should be a really quick check. If the original is a function, you're looking for the vertical line test. If the inverse is, it's the horizontal line test. Now look at these points. The point here is what? 2, 2. And this point is 4, 2. So if I didn't have these issues, if I could cover up these, the original graph would be a function. Agreed? Because every x has one y. But if I would flip my graph, do you see that this y value of 2 has more than one x value? And if the inverse is flipping x and y, that would make my new x's have more than one y. Now, hopefully this comes together as we keep working, okay? Okay, so it says to find the inverse of this function. Okay, now listen, we're getting up there, right? Like when we did inverses before, we weren't dealing with as much. So let me remind you about the idea of finding inverses. When you go to find the inverses, there are, I'm going to say 3 steps. The first step is to switch x and y. So write this down to help you remember. Switch x and y. That's the first step to finding an inverse. Switch x and y. Okay. The second step is going to then be to solve for y. And then the third step, I always say, is to rewrite. Rewrite in function notation. Now, we have already done this. Switch x and y. We did it when we introduced function notation, when we were working in function notation. So here's what I want to show you. The original function f of x equals the cube root of x plus 1. So when I say switch x and y, I do need you to remember f of x is the same as saying what? Y equals. So I'm going to break it out of function notation, and I have y equals this. Now, I know it seems weird, but we are going to break this out. So you're going to have, or switch x and y. So x equals the cube root of y plus 1. Okay, so that was step 1. And put a little 1 beside it to switch x and y. But I wanted to remind you that we replace f of x with y equals. Now, the second step is to solve for y. So what should I do first to solve for y? I need to get rid of the cube root, and I need to get rid of the plus 1. Do you notice that that's in here? So this is like it's in parentheses. You can't do that until you get rid of the square or the cube root. So what cancels a cube root, guys? Cubing it. We did this before. They were more linear. Now, if I cube this side, don't I have to cube this side? So my cube and cube root cancel. What's nice about this is I don't have to like multiply it out a bunch of times. It's just x to the third equals y plus 1. So I'm really working on step 2 at this point where I'm solving for y. And to get y by itself, I would do what? Subtract 1. So step 3, rewrite in function notation. Well, I do have y equals x to the third minus 1. So in function notation, it'd be f to the negative 1 of x equals x to the third minus 1. Now, I still have more to do with this. Okay? Oh, you can't see. You should yell at me. So the reason I think it's really important to show the original function as f of x, because you have two things going on. Here's my original. Here is my inverse. And you notate the inverse with the f to the negative 1. Do you see it? F of x, and this f negative 1 has nothing to do with the power properties of flipping. It has to do with, hey, this is the inverse of f of x. So inverse of f of x. Okay, now, to determine if these, determine whether these are functions, state the domain and range. Okay, so one of the things to determine if this is a function, first of all, I can put anything in here for x because I can take the cube root of positives or negatives, and I'd only get one outcome. So this first one, f of x, the original, it is a function, okay? It is a function. Every x has exactly one y, or if we graphed it, it'd pass the vertical line test. Every x passes, oh, every x has exactly one y. Every x has, and the reason I'm willing to say it and write it again is so we remember it. Exactly one y. Okay, now, the domain, well, I can put anything I want in here. There's no limit to what I put in, no limit to what I take the cube root of. So the domain would be negative infinity to infinity. I can put anything in. And the range, well, I can get anything out. So cube roots are very forgiving. If it was a square root, that'd be a different story. Okay? Now, its inverse, f negative 1 of x, it is also a function. Whatever I cube will come out. If I cube positive 2, I'll get 8 and then subtract 1. If I cube negative 2, I'll get negative 8 and subtract 1. So anything I put in, I will only get out one answer. There's no plus or minus sign here. So that is a function. Again, you could test it by graphing it real quick. Every x has exactly one y. So to graph it, you could use a graphing calculator. You could use something like Desmos online, and you could see it passes the vertical line test. Again, the domain, anything can go in, and in the range, anything can come out for y. There's no limit. There's nothing that would make it undefined. You will talk a lot more about domain and range in calculus and pre-calculus, okay? All right, ready? So find the inverse of this, very similar idea, and then determine if they are functions and give the domain and range. Okay, so the original guy, was f of x equals x to the third minus 2. Now I'm going to rewrite that as y equals. You could skip one of these steps and just jump in, but I want to remind you this is y equals. Step 1 to finding the inverse is to switch your x and your y. Step 2 is to solve. Okay, so what should I do to solve for y? Add 2. So I get x plus 2 equals y to the third. Then what? Well, how do I get rid of y to the third? I'm going to cube root it. The square root gets rid of a square. The cube root gets rid of a cube. So this is going to cancel, and I do have the cube root of x plus 2 equals y. So what is my inverse? It is the cube root of x plus 2. Okay, so there are my two functions. And these have the same rules, guys. No matter what I put in, I will only get one outcome out, okay? No matter what I take the cube root of, I only get one outcome out. So for every x, both of these are functions. So f of x is a function. Okay, every x has exactly one y. Domain is still any input, and I will get out any real numbers from the output, so all reals. And its inverse is also a function. And it would be the same thing. So if we were doing more work on this, we would find some problems would have domain and range issues, such as square root. If you had a square root, your domain would be whatever's underneath the square root has to be greater than or equal to 0. So we made this a little more basic. All right, so we're fully paying attention. No one is on their phones again. When a relation and its inverse are functions, so when they're both functions, like these were both functions, then it's called to be a one-to-one function. One-to-one function. In a one-to-one function, each y value is paired with exactly one x value. It's the idea that for a function, every x has exactly one y. Did you guys remember that sometimes the y's could repeat? So if I gave you a chart like this, x, y, and I had 1, 2, 3, 4, and this was something like a 2, 3, 6, 8. Well, every x has exactly one y, but if we flip-flop it, if you flip your x and your y, and it becomes 2, 3, 6, 8, and then 1, 2, 3, 4, do you see that still every x has exactly one y? So this would be a one-to-one function. No matter how I look at it, both of these are functions. Now, so these are both functions. This would be 1, 2, 1. If I gave you another example, and it was something like x, y, and x is 1, 2, 3, 4, and y is 5, 5, 5, 5. A lot of people would look and say, oh, it's not a function. It is. Every x has only one y. It's okay that the y's repeat, as long as the x only has one outcome. But if I flip the x and y, what happens? Well, this x value of 5 has more than one y. So this is a function. This is not a function. And overall, it is not a one-to-one function. That's all it's saying. It's a one-to-one function if both the original and its inverse are functions. Okay? That's the idea. Now, we are going to change ideas here, and we are going to use what we know about compositions to see if they're inverses. So the compositions of two functions equal the input value, or x, if the functions are inverses. So if the composition f of g of x equals g of f of x, which equals x, then these are inverse functions. So there's going to be times where you're told, hey, find the inverse. And if you're told to find the inverse, you flip x and y, you solve for y. I found the inverse. But there's times that you're going to be asked to find to find if they are inverses. you can't just find an inverse and say, yes, they're the same. You actually have to prove it. And so you basically prove their inverses by composition. So let me give you a function. F of x is 3x. We'll go real basic here. And g of x is 1/3 x. So I'm giving you these two functions. I'm not saying they're inverses. I'm asking you to prove it. So the first thing you're going to do is take f of g of x. And remember, your compositions, the order matters. So when I go to do this, I'm going to take g of x, which is 1/3, and put it in for x. And you see that the 3 and 1/3 cancel when I get out the input. Now flip-flop it, reverse your composition, and this time, bless you, I'm taking 3x and stuffing it in g of x. And g of x is 1/3 times x, which is 3x. And that 1/3 and 3 cancel and I get out just x. So this is an example where f of x and g of x are inverses. Now, if you're pretty comfortable with compositions, this is pretty good. Compositions is normally not the problem. The problem is we look too quickly and we see what we want. So you have to be careful with the algebra. So we are going to determine by algebra if these are compositions, or if these are inverses, by using compositions. So if you look at this one here, it says determine by composition whether each pair of inverses or each pair of functions are inverses. So you're going to have to do two compositions. So guys, I don't want you to take this and find me its inverse. You wouldn't get credit for that. You have to actually show and prove it. So what you're going to do is you're going to do f of g of x, and then you're going to reverse the composition to f of g of f of x. Be good if I could talk. So whatever you need to make your compositions work, if it helps you to drop g of x down 1/3 x plus 1, please do so. Okay, now take this g of x and stuff it in here. I'm still suggesting when you do your compositions, you pretty much rewrite the function and drop that new function in after you're done. So I'm dropping in the 1/3 x plus 1, and if I follow the order of operations, I would distribute this first, and that's where we make the mistake. A lot of people are like, oh, 1 minus 1, and 3 times the third. This distributes, guys. I do get x, but I get plus 3 minus 1. So I end up with x plus 2. So f of g of x, does that equal x? Did it cancel itself out? No. So I'm done. These are not inverses. F of x and g of x are not inverses. Now, if the first one doesn't work, I don't have to try the second one. I'm done. Okay? If the first inverse doesn't show, or the first composition doesn't show that they canceled out and I just got x, then I don't have to test the second one. But both of them have to be true to be inverses. Now, I'm going to test the second one just for good measure, just to practice it. So put 3x minus 1 in here. So it's 1/3 and then plus 1. 3x minus 1. Do you see what I'm talking about? If you look at it too quickly, you're like, oh, look, there's x and the ones cancel. But if you actually follow this and you're not thinking ahead, you'll see that I end up with g of f of x equals x plus 2/3. So unless it equals x, they're not inverses. All right, so let's look at another one. You have some fractions in here. So notice that you have x can't be 1 or 0. Those are just your domain restrictions. So first, let's find f of g of x. And then next, let's do g of f of x. Okay, so what's going on here? I'm going to take g of x and plop it in there. So it's 1 over x minus 1. All right, well, g of x is 1 over x minus 1. I don't need these parentheses here. There's nothing to distribute. So I really have 1 over these. This should be plus, shouldn't that be plus 1 in there? 1 over x plus 1. These ones are going to cancel, and I'm left with 1 over x. Now, hold on a minute. You can't leave a fraction in there, right? Don't we keep, change, and flip, or multiply by the reciprocal, and I get out x. Okay, it's looking good because these canceled out and I got x. Now, flip-flop it. Take this and put it in your denominator here. So you have 1 over x and then plus 1 attached. Okay, so this goes in as 1 over x minus 1. Guys, I can't add or subtract. I have to deal with this. So this is really 1 over 1 times the reciprocal of x minus 1 over 1, and then keep my little plus 1. Okay, well, when I distribute this 1, don't I just get x minus 1 over 1 and then plus 1? That cancels, and again, I just get x. So do you see that both ways that I do the composition, I get x out? So that means that f of x and g of x are inverses. So yep, they are inverses, and I've proven it. All right, so that is what you're looking for every time. So if I said, here's f of x, find me the inverse, that's when you flip x and y. But if I'm asking you to prove their inverses, f of g of x, g of f of x. So I'm going to do both of these. So I'm going to take this and tuck it in here. So it's 2/3 times x plus 6. And maybe I'll even put this in a different color. I'm dropping in the 3/2 x minus 9. So when you guys are thinking about this, the parentheses are key. When I distribute this, that's 6 over 6, or just 1x. And 2/3 of -6 or -9, that does not cancel out. What do I get there? Am I doing 2/3? So, I do get -18 over 3. So that does cancel out to -6. And then plus 6. Oh, look at that. I got out what? X. Okay, so it's looking good so far. Now let's reverse it and see if it works. So sometimes one will work, but the other won't. Sometimes they both work or both don't work. I am going to take my f of x and stuff it in there. So here I go. This time it's 3/2 times x minus 9. And inverses can be tricky. Sometimes they look like inverses and they aren't. And other times you're like, how is that its inverse? And it is. So I took f of x and I stuffed it in there, and I'm going to distribute. Here again, these would cross cancel, or 6 over 6x. So I have just x. 3/2 times 6, well, that would reduce, but it does give me a positive 9 and then minus 9. If you need your calculator for your fractions, that's fine. But the 2 would cancel and leave me 3 times 3. These cancel, I get x, so boom, these are inverses. So f of x and g of x are inverses. All right, so let's prove that these are inverses by taking the compositions. So I'm going to do f of g of x and the reverse, g of f of x. So here we go. I am taking g of x and stuffing it in here. So it'd be x squared plus 5. And then let's go ahead and drop in g of x. And we have to be really careful here, because as much as we want to just jump in and square both pieces, we can't. You actually need to FOIL this, which can be a little bit messy, but we are capable of it. So if I FOIL this, I get the square root of x squared, which is going to cancel. I get a -5 square root of x. I get another -5 square root of x. And last, I get a positive 25 and then plus 5. So this cancels and leaves me just x, but I'm left with a minus 10 square root of x and then plus 30. So in no way, shape, or form does that cancel out. So f of g of x is x minus 10 square root of x plus 30. And that did not cancel out and leave me just x. So I can tell you right now, f of x and g of x are not inverses. All right. So I would pretty much be done. I don't have to go further, but because we're doing this as a lesson, I'm going to go ahead and do the reverse. I'm going to take g of or f of x and put it in here. So it'd be the square root of x, and then on the outside minus 5. And the f of x that's dropping in here is x squared plus 5. Now, same issue. We break these rules. A lot of you want to cancel the 5 and negative 5, or you want to say, oh, this is the square root of x squared is just x. I can't break down this root. So this is actually my answer. It is the square root of x squared plus 5 and then outside minus 5. You can't cancel these. That's not part of it. So again, this just proves that these are not inverses. So if f of x and g of x are inverses, they will cancel everything out just like multiplication division, and I'll be left with just x for both compositions.